that goes.
Okay. Try it. Okay. Well, thank you very much for coming, and welcome back. Some of you, I see friendly faces from last week, and welcome to others for the first time. It's my pleasure to introduce Dr. Jean-Claude Bradley from Drexel University. He's an organic chemist by trade, and this has certainly been part of his work. But I know him only from a web presence and from his publications and from his website that he has been an incredible leader in open science notebooks, but open science in general. And I felt that it's important for us in kind of this interdisciplinary kind of gathering to address issues of openness, that we have open access, we have Creative Commons, we have notions of copyleft publications, etc. The conversation in academia is changing quite enormously, and I think that one of the things that Dr. Bradley has done for us that I find enormously important is given us kind of a taxonomy of openness, and I'm hoping he'll speak to that today. So thank you so much for coming.
All right.
Appreciate having you here. Thank you.
Thank you so much for the invitation. So I would like to talk to you today about the value of openness in research and teaching. And this will be brief. I was told about 20 minutes, so I'm going to skip over a lot of the details, be happy to talk about it later in terms of technical implementations. But hopefully in 20 minutes you'll get an idea of what can be done. And also the surprising things we never expected would happen when we simply made the decision to go open. And one of the most surprising things is that, you know, when you're a faculty, you have to do research and you teach. And the one thing openness has surprised me, it acts as a kind of a conduit, a bridge between research and teaching. And that's something that I didn't really expect that worked out. So I warn you, there will be some chemistry. I kind of have to because I want to give specific examples. It's not important that you necessarily understand the chemistry, but you need to understand that as a chemist, I found a problem. So in your field, as a biologist, as a mathematician, whatever, you found a problem, and these are the kind of ways that I addressed it using openness. So I teach undergraduate organic chemistry, and last year, for the first time, I taught organic chemistry lab. And one of the reactions that we did made this compound, dibenzylacetone, DBA, and the lab required a, yes?
Oh, we could do that.
We definitely could. It's on the monitors in front of everyone. We can turn on the large one too.
Okay. All right. So yeah, so I was starting to teach this lab, and the students had to make this compound, and they said that they were using ethyl acetate to recrystallize this compound. Again, it's not important you understand, you know, why that's surprising, but as a chemist, and if there are chemists here, that might be surprising given that the reaction is done with water, and ethyl acetate is not miscible in water. So that didn't make any sense to me at all. And furthermore, a good part of the class could not reproduce the synthesis. And so I kept wondering, how is this possible? So I started to research this a little bit, and I started to think, you know, why are they using ethyl acetate? For one thing, the synthesis of this particular compound is widespread in organic teaching labs. All around the world, this lab has almost certainly been taken by students. And the methods vary. We looked at the different ways, but ethyl acetate is very often used to recrystallize this compound. And as I kept tracking back, it turns out that eventually you get to this paper from 1903 that used ethyl acetate for no reason. And everybody's been using it since then, you know, just because it was there. And then I tried to see, well, you know, is this logical? You know, what is the solubility of this compound in ethyl acetate? And it had never been reported. In fact, there was almost no solubility measurements whatsoever. And so there was no rational way to pick a solvent to do this. And so that's when we started. Luckily, I had an outstanding undergraduate student, Matthew McBride, and he had just started in my lab. And I asked him to start working on this to measure the solubility of this DBA, this compound, and try to repeat the experiments. And a lot came from this. That's just one of the poster sessions that he gave. He presented at the American Chemical Society, an oral presentation. So this really worked out well in terms of a student project. But we learned a lot from it as well. So we talked a little bit about the concept of open notebook science. So what that means essentially is, as a chemist, you have to keep a lab notebook. And what we've been doing since 2005 is simply saying that notebook has to be available in real time to the entire world. So that includes the notebook, all the associated raw data. The idea is there should be no insider information. People that are following our work should have exactly the same access to the stuff that we know inside behind our group. And what happens with that is, of course, most of the things that end up in the notebook are what you might call a failure. I have a little bit of a problem with that term because sometimes you get something else you didn't expect. It's a failure with respect to what you were trying to do, but it's not a failure because you discovered something. But let's just suffice it to say, not successful reactions. And we could actually measure this. It's about 87% of not successful reactions. So this is another thing that enables you to follow how science works by looking at all the stuff, not just the stuff that works. So this is not the notebook yet. This is a summary. And this actually comes from the fact that we also represent the information in the notebook in a semantically aware fashion so that this is generated by a query based on what we categorize this at. But I'm showing this particular example because it's what you would call a failed experiment. Matthew actually tried to do a reaction here. In this particular case, it was ethanol water 1:6 ratio, and it completely failed. And this is something we were a little bit surprised because we got a bunch of procedures from lab manuals from around the world, and not all of them actually worked. And it might be because of a typo. Whatever the reason is, they didn't work. And so the problem is that no one publishes this. Okay, so now that we've essentially published it in the sense that any chemist looking for this should find it and they should see, oh, I shouldn't use that ratio. But more than that, when you click on the link to the actual lab notebook page, you see every detail. So this is a very small part of the lab notebook page, but it shows you the important stuff. You've got there's a discussion, all kinds of stuff that I'm not showing here. But I highlighted in red in this log section, which is where the student records what they did or what they observed minute by minute. All right, and we can see that the student observed, I don't know if you can see it on your screen, it's a little fuzzy on mine, but it says that 2 layers formed. And what that tells me is that the compounds we were trying to mix were not soluble in this mixture. That's actually much better than just saying it failed, because this is real information that you can react to. And in fact, when we changed that to 1:1, it worked very well. We got 87% yield, and in fact, this worked so much better than the procedures in our lab manual that this is now going to be adopted next term. My student's procedure, in fact, the compound is so pure there's no need to even recrystallize it. It just comes out. So this is like a good example of where openness actually can enable you to connect between research and teaching. Okay, just to give you sort of a contrast about, I don't know if there's any chemists here, but if you're looking for chemical information, you're trying to make something, just because you find it in a paper doesn't mean that it's easy to reproduce. This is kind of an extreme example of this. This is a related compound, it's not the same one. But basically, the only thing said in the paper is, we followed the procedure of so-and-so. Unfortunately, so-and-so didn't make this compound, they made a similar compound. And so this is rare. I mean, usually you get some information, but you never get the entire story. You never get to see all the failed runs. And when they report a yield at 90%, what does that mean? Does that mean the best yield they got? Does it mean they averaged? What did they do if they gave an undergraduate to do it and they got 5%? Did they throw that out? Well, that is completely obscured in our current publication process. And by the way, this doesn't replace our publication process. These things get published, but day by day, the world can find out what's going on. So if we're talking about open notebook science, that's a little bit. And there's more on a Wikipedia entry if you're interested. So where do we go from here? Well, we didn't stop at dibenzoyl acetone. We actually pushed it further, where we created an app that would work on smartphones or laptops, whatever, that would actually you could actually put in the compound and it would tell you what solvent to use to recrystallize. So this is what it looks like. You literally just type in your compound, like benzoic acid. There are default settings for what we found works. And this is what you get. Basically, this one gives you 4 solvents. And if you click on the solvent, it shows you a temperature solubility curve. So if you were to heat this, how much of it should go in? So this is actually very useful. It's something that wasn't available to the chemistry community, even as far as I know in commercial software, and this is completely open data. And the only way that we were able to make this is by using essentially a mashup of a whole bunch of open data feeds. And this is really the key with open data, is that our output is open. That means we cannot take anything that has any restrictions on the data set. So I mean, we've tried to get data from companies who might say, well, you can use it, but, and then, they might have some special clause, can't use any of it because we can't, it'll contaminate the rest of our data set. So this is why staying open, true open data, CC0, I'm not sure if you guys are into those terminologies, but it has to be absolutely open. People can use it for any reason, even commercial reasons. I know some people have a bug about that, but yes, we had someone who used our feeds and then sold an app, and I have no problem with that. I encourage it. It's just, it makes everything so much easier. Okay, so there's a bunch of other things here. For example, if you hit on the melting point button, you can get a melting point, you can get a predicted number, just sort of flashing through here. So I'm not going to go through the details of how it works, because I don't have time. But suffice it to say that it uses data from our open solubility collection and our models. It uses our open melting point collection and models. And we use what's called the CDK, the Chemistry Development Kit. This is an open source system with open algorithms. And again, that's important. It's not just the open data. You have to make the algorithms open so that people can see how if you build a model, they can actually see how you did it. Surprisingly, that's not actually the norm. People do use commercial packages, black boxes, and they say they have a model, but you can't see how it works because the algorithm's not open. So what does this look like? So basically, we keep everything on a wiki, a series of wikis actually. Wikispaces is my preferred one. And yeah, basically every collection we have of open melting points will be on this page, with a link to the file and a description of it. So as we merge data sets together and clean them up, all of that is recorded in that process. So it's actually kind of interesting how this melting point project started, because if you were looking for open melting points, you would be hard-pressed to find more than about 4,000. And as of this date, we have 27,000 completely open melting points. And that's actually made all the difference, as you'll see in a minute. But how this all started is I teach chemical information retrieval. And the purpose of that class is to show students how to find chemical information. So a simple example would be, how do I look up the melting point of methanol? Right? Well, the students always say, just Google it. And there's actually some validity to that, but there's a lot more to it. So that's what I show them, is how basically that there's no such thing as a trusted source. No matter how glorified a source is, we've found errors in all of them. And the only way to find out if you have an error or not is to get enough measurements of the same thing. There's no shortcut to it. So basically, I've been collecting, students have to do 25 measurements for a compound, and they've been putting them into these Google spreadsheets. And then at the end of the term, these Google spreadsheets get merged into the larger data sets. And never trust the students, so they have to provide an image of where they got the number. If they don't provide an image, we cannot use that number. So we have to actually go through each and every entry and assume that they made a mistake somewhere. But the advantage is, if you actually have the image and you can evaluate it, the quality of your data will be better than anything else that you can do. Now, again, I talked about surprising things, what happens. Well, this really surprised me. The first term that I did this, I was blogging about it, And the second most common source for chemical information is from this company, Alpha Acer. And this is a chemical vendor, so they're not involved in providing chemical information, but it turns out that they're highly indexed in Google for a number of reasons. If you're looking for a melting point, that was your second choice. The first one was also a company, Sigma Aldrich. And the VP for marketing contacted me and said, you know, I saw your post about our company. Do you want to do something collaborative? And I said, yeah. Can you donate all of your melting points to the public domain? Can you make it open data? And they actually said yes. And so we got about 10,000 melting points, which was unprecedented. But the thing is that, I don't know if you can see from here, this wasn't an actual database because those are not numbers, those are just text. So there's ranges, you have letters like CA, circa. So we couldn't actually just plug this in and start using it. We had to do a lot of processing to clean it up. And so one of the things we could give back to them, a cleaned up database, an actual database with values, in addition to the rest of the world. So I was telling you about how you cannot trust any particular source. Well, we got actually donations from a bunch of other groups, the EPA as well, the FISPROP database, and that's how we ended up with 27,000. And for some compounds, we got a lot of measurements to compare. So here's ethanol, right, one of the simplest organic compounds around. And again, I don't know if you can see that on the screen. You can see it here. Okay, so basically, most of the values are very, very close to -114. But they're not exactly the same for the most part. That was the other thing that we found out the hard way. If you have two values that are exactly the same, they probably come from the same source. And so after the first year of doing this, I would not allow a student to repeat a number if it was exactly the same. That's one of the real problems today. If you Google something, you'll get a number, 90 times. That doesn't mean anything because these databases copy each other all the time. So as long as you have an actual different number, then we consider it has to come from a different source. But what's interesting here is two of the numbers, right, -130, -144, one of them is actually from Alpha Acer. And it's clear, hopefully, to all of you that those are the two outliers, right? It's very unlikely that everybody else is wrong. And, I called them up to find out. I mean, this is a very, simple compound. And what happens is they copy information from catalog to catalog, and there's no provenance necessarily as to where. So if somebody made a mistake at some point, that's it. It'll keep in there. And you'll notice these in red. So we never delete data from any of our data sets. What we do is we mark them as do not use. So that means that when the calculation is done, it doesn't take into account these outliers in the average. There's a good reason for doing that because we don't want people repeating our work year after year after year. By actually putting it out there and marking them as do not use, that's it. This is the entire data set. And you make your own decision as to, if you want to use it or not. I'm telling you which ones we're not using, but you could decide to use them if you wanted to. Okay. So this was about 2 years ago. I just taught this class last term. And now we're actually getting to the point because we have these models for melting points for solubility. And we can actually take the outliers from these models and assign them to the students to look up values from literature. So the students have to look up 25 values anyway. Why not give them something useful? So in doing this, the students are effectively creating new science. They're actually addressing a particular model, and they're finding out is this an outlier because the model isn't great in that chemical space, or is it an actual outlier that we need to mark as do not use? So this is the direction that we're going in terms of merging teaching with research. So I'm just going to sort of fly through these. These are just basically ways of accessing the information. So we have an Open Melting Point Explorer where you can do a substructure search. So these are not just numbers they are actually numbers in a Google spreadsheet, but the software understands what chemical compounds they are. So if you want all alcohols, there's easy ways of searching all alcohols. And this is just one of the web interfaces. Here's another web interface for reactions. So you can search by compound, by solvent, by student. It's a web interface. This is with Andrew Lang He's actually a mathematician at Oral Roberts University, close collaborator. He basically did all the computations for the stuff that I'm showing, and this is an excellent model based on the open data set that we have. And if, let's say that you want to send somebody the melting point of caffeine, which actually happened to me a couple of weeks ago, I can send you a link that's dynamic. That means that if we find a new measurement, it'll automatically be added to this. So we've created it so it's easy to share real-time information. And you can even get a summary. You can say, for vanillin, give me all the solubilities and all the solvents that we've ever collected. And that's just one link. So we spent a lot of time trying to figure out how to not just collect the information, not just make sure it's public, but also make it easy to access depending on your purpose. So here's probably the most interesting one for some of you. This is where we're using Google Apps Scripts. Anyone using these so far? These are really neat. Basically, you have a Google spreadsheet, and probably about a year ago, Google gave the capability of writing your own script, create your own customized functions. And that's really neat because if I'm planning a reaction, see those images of molecules, I didn't draw those out. Those are actually a web service call that we basically just, there was a command get image. And so you can just lay your stuff out, and if you want the molecular weight, if you want melting point, any of that, it's basically, you just have drop downs, right? So these are all the different drop downs. So get MP would be get melting point, and that's it. You click on the cell, hit get melting point, and it will appear for you. So I think this is probably the most useful thing that's come out recently because obviously this is not just for chemistry. You could use it for any field, and it's really, really nice what they did. Again, it's completely free. Students don't have to buy software. All they have to do is to go copy a template. I'll give you a link where you can get that, but yeah, just go copy the template. You automatically have all of these scripts and to do what you want. So for example, let's say that you want to explore alcohols going from 1 carbon to 2 to 3. How does that affect the melting point? That would be a tremendously time-consuming thing to do, assuming you wanted to get numbers that you thought were reliable. Now, if you just wanted to Google a couple of numbers, that's one thing. But if you wanted to be fairly certain that they were close to the truth, we can now do this with the Google Apps Script because when it gets to the melting point, it also gives you a link to all of the data sources that combined to give that number. And so you can find out if you should have high confidence in that number or if the number could be random. And so that's something using the Google Apps Scripts that is good. You can also link to NMR spectra, any kind of 2D. Here's another thing. If you look in Wikipedia, we have the melting point of ethane. This is pretty obscure stuff. This is actually in the table that's behind Wikipedia, and it would be almost impossible to know for sure that that number's wrong. But because we never throw out any data, we know that that minus 172 is wrong, and the number should be minus 182. And that would be insanely difficult to do without these tools. So you can see the problem here is that students writing up reports, they're going to go here, they're going to copy minus 172. That's going to go in a report, and then this gets copied. So again, there's no shortcut in trying to figure this stuff out. So Google Apps Scripts, if you're interested in them, it's a wiki, onswebservices.wikispaces.com. And if you want to play with them, you just make a copy, and you'll have all the script. We have a sheet that has a detailed description of every service that we've made. Most of these are by Andrew Lang, and it tells you what the input should be and what the output is going to be and the limitations of each if you're not sure how to use them. So finally, going forward, our plan is to basically expand what we've done with melting points, with solubilities, to pretty much any chemical property that we can get our hands on. I like to explain it in a sense that you forget before the Google Maps that you couldn't just go online and get a direction. You forget that, but that's the way the world was pretty recently. And I think chemistry is going to be the same way. Maybe 5 years, if you have a compound, it will know what its likely melting point is. If it's a drug target, it'll just know in the same way that Google Maps knows where for you to go for the most part. So this is really the vision here is to make this completely open so that it gets solved once and for all chemical properties. So in conclusion, I hope I've shown why there is a selfish reason for doing open science. You leverage more what you do. I mean, the students like that if they're in the lab one day and they get a solubility, that someone from DuPont the next day could be using their result. And we get about 300 queries a day for specific solubility measurements. So, and we get hits from companies. And so it's basically just for the student to represent themselves, what they can do, and have their work used. I think it's tremendous. And the key thing here is, if you're interested in this kind of thing, provide interfaces that actually make sense to the end users. So what I mean by that is if you have a model, write it up in a way that modelers can understand it. But if, for example, I showed the recrystallization app, the organic chemist shouldn't have any idea about how it works unless they want to. And that's something that takes time. You have to actually design it for different users. And you have to make it super easy, like I showed you, where you just type in benzoic acid and hit a button. It has to be that simple, I think, for any of this to actually catch on and start being used. And that's actually, that app is going to be used in future organic chemistry labs at Drexel. Because one of the problems is right now with organic chemistry, it tells you use this solvent, recrystallize from this solvent. What I'm trying to have them do is not put anything and give them the app and have them think about what solvent they should use. And they might not all choose the same thing, and that's fine. So at least they're thinking instead of following a recipe. And so that's really the direction that we're going in. So that's it.
Thank you.
Thanks. Yes.
Just a point, since this is out there everywhere, I know that in the first 2 weeks of freshman chemistry, one of the things they talk about is significant figures. And you report melting points to 5 significant figures. You have things, 6, 7 significant figures that obviously are more than is appropriate. And I was wondering, have you thought about trimming those down to numbers that are appropriate to the experimental sources?
Yeah, that's actually an interesting point, because you teach students about significant figures, but the reality of the melting point world is people add numbers all the time that are not significant. And we made a decision basically to not take significant figures into account at all. So sometimes the way that the web service works, it'll report a bunch of numbers, and that's not just us, by the way. If you look for any of these prediction services, one of the telltale signs that it's from a model is there'll be a whole bunch of numbers that can't possibly be real. So yeah, we struggle with that, but I mean, you can't go back and tell everybody to go back to the lab and give you the correct number of significant figures. So we're kind of stuck with that, and it turns out that the error for a melting point is kind of within, what would matter for the significant figure anyway.
I mean, could you truncate those and just say automatically, you're never going to get more than 5 significant figures?
Yeah, I mean, I don't know what you saw, but yeah, we definitely truncate them depending on, perhaps in that case, see, sometimes the solubilities are like 10 to the minus 6, and we had a problem that it wouldn't display. That's probably what you saw, and so we just made a decision to do 6. So that's probably the reason that was there. But you're right. I mean, you should not interpret that as being accurate to any more than a degree or so, if that.
I guess just a comment. I'm just listening to you, and I think that this is a really great way to sort of publicize what we are doing in classroom to the whole world. And especially in chemistry, there's so many fundamental things that we can learn from one another. And I'm working on some sort of bioassay as a biologist, and in classroom, sort of, mini research. And I thought maybe I can just see myself in a spreadsheet with all the different environmental toxins, the effects on this, or type of a measurement of a bioassay and all the different animal species. And I thought, oh, maybe. So what do I need to do? Do I really need to get into this spreadsheet, or I mean,
yeah,
I don't really use
I didn't talk about this at all, but right now, Matt, so these dibenzyl acetones, we're making a whole bunch of derivatives. We're making like a virtual library, and we're looking for, for example, Taxol receptor. We've actually we've done some docking and things like that, and so we've made compounds based on that. But yeah, building models that would predict IC50s for a bunch of enzymes, that's definitely on our list to do. So, I mean, our limitation is basically because we're an organic chemistry lab, the assays are not that convenient. But if we could partner with some people that, you know, would do the assays, then we'd be happy to do the synthesis. So yeah, definitely. And we want these things to be open so that other people don't have to reinvent it every time. So yeah, definitely.
When you talk about openness, that means that also other university can contribute and upload data?
Yeah, I mean, anybody can contribute. In fact, the Melting Point project started as Open Notebook Science Challenge, and we got a little bit of funding from SubMeta and the Royal Society of Chemistry. We just gave out an award. Matt actually just won the last award. It's $500. It's not a huge amount, but it is an award that, you know, they can put in their resume. This is the 12th one that we've given out. And the first winner was actually from the UK. So that was a whole other experience of setting up a contest legally. That's why we could only do it in the US and the UK, because it would have been too expensive for the Drexel attorneys to expand it to Europe, for example.
So this project is not funded?
Not funded from NSF. Yeah, I was trying to get some feeling about it. NSF doesn't seem to want to fund contests. You know, that's a completely different model. And even that was sort of an interesting approach with the funder, even though the amounts are fairly small. You know, I was telling them, you might be tempted to say, okay, we're going to give you, you know, $10 per melting point. Here's the problem. If you do that, it's going to be garbage. So instead, the criterion was how good of a scientist were they. They might have only done one melting point, and that turned out to be a very difficult thing to do. As long as they recorded their lab, their experiments, you know, correctly, the log, they interpreted them correctly, and they were responsive to comments from the judges. And that was something that people really didn't, it was sort of a different model, okay? And so this is not a production kind of system. You have to be extremely careful when you have rewards, because people will give you whatever it is that your metric is. And that's not necessarily what you want. You want people to be honest. You want them to basically just do good science. And I can easily see that slipping through, you know, if you paid them $10 per melting point. So.
I'm sorry, just the last comment. I don't know. It's very interesting, and actually I am a TA in design, leadership, and creativity. So like we usually look at the feasibility also of a design process. So I was just afraid that this beautiful project, you know, at some point, you know, can just stop because, you know, like availability of funds, because as you say, there is, these data are so accurate, but at the same time, to be so accurate, there is a tremendous work behind, right?
Yes, and that's why I was talking about this a little bit before, the fact that Alpha Acer donated 10,000 melting points. That's where the real gold is, in my opinion. And it's interesting because I approached other chemical companies and they will not do it. And I think that's actually a huge advantage because I talk about them today. I talk about them every time I give a presentation. People using our service, it clicks through to their catalog. I mean, they have absolutely nothing to lose to make it public, but, you know, I think most companies just sort of have this reaction, this automatic reaction. But I think if we're talking about monetization and, you know, where that can go, that's actually, the companies are sitting on a wealth of information, and if they make it open in the right way, I think they can benefit. The point is too that at some point you don't need them anymore. Like for ethanol, right? We have so many sources now that it kind of doesn't matter if another company donates. So you would be better off being one of the first to donate because you're going to get the most exposure. And so, yeah, it is interesting how this is developing. And once you take the genie out of the bottle, it can never be put back in. Yeah. And that's the really nice thing.
Thank you.
I can imagine that pharmaceutical companies have thousands and thousands of molecules that they know the melting point on that you can't get. Do you have any idea how large your sample is compared to the world of known compounds that's not available? I mean, are you talking about 1% of the information that potentially could be in your database, or is it larger?
It's hard to tell because, I mean, pharmaceutical companies will never even tell you what they've measured. I mean, there is this concept of pre-competitive sharing, And something like melting point and solubility would make sense. People are talking about it. They may have been doing things, but the things that I've seen, there's still some restrictions. In other words, they might share with each other, but not the world. And this is really the key point, is that there's no partially open. Even if you share with a fifth of the world's population, if it's not absolutely open, you can't do these things. Like, we can't incorporate anything that you provide unless it's completely open. And so if you have any restrictions, so I think that's what's happening, is that you do have these large databases that are localized, but if I can't use them, then they don't exist really in my world. So I don't know what the answer is. But the nice thing about the melting point project is you don't have to get every melting point that's ever been measured by anyone. At some point, you end up with enough numbers that your models are pretty good, and that's where we are right now. So our estimates, so we don't need all of the databases. It'd be nice, but we're not waiting for them. You just have to get to a point where you can get a good enough model for the chemical space you're interested in, and then who cares after that point? And so I'm very, very pleased with the model that Andrew Lang has been able to build. Used the random forest approach, and we're getting better correlations than pretty much any of the other models that we've looked at so far. So that's the end game, in my opinion, is to get enough to get a model, and then you're done.
So are you at the stage where somebody can put in a molecule that is not in your database and have it predict?
Oh yeah, well that's how the recrystallization app works. See, it has to actually predict. It'll look up, if it knows the melting point, it'll use that. If it doesn't know the melting point, it'll use the model. And then for solubility, it does the same thing. It's looking for the room temperature solubility, and then if it doesn't exist, it uses the model. And so that it always returns something. And so far we found that it's close enough that, yeah, it works. If it's off by 30%, who cares? Because it'll show you that you're in the right ballpark. But yeah, without models, there's no possible way you could do a recrystallization app, because you'd have to measure every single solubility, and we have 100 solvents that we use. It's impossible. So yeah, I don't know if maybe I didn't make that clear, but prediction is absolutely key to all this, and especially open prediction, where anyone can repeat, can use your algorithms. They know how they work, can modify them. That's something that is a little bit unusual in the modeling space, and I'm hoping that's going to change in the next few years as well.
I'd like to move us to a discussion of what people have done in terms of openness, in terms of classroom or considered. But first, you've, in some of your interviews, been critical of some crowdsourcing citizen science projects that people have been exploited and that it doesn't fit with your model. And I was wondering if you'd elaborate a little bit on that.
Well, the term crowdsourcing is a little nebulous sometimes. I would consider it where, everything is open. You have models where it's people, for example, can see the questions, but when they submit a solution, no one can see it, and you know what I'm talking about. People get paid for these things. There's nothing wrong with that, but I'm just saying that in terms of really leveraging crowdsourcing, once you make everything open, and obviously if you do that, then you can't be promising people huge amounts of money. So the money question is actually very interesting. It's because there's no money in it that it works. There have been studies done about this, that the higher the reward that you provide, the worse the creativity becomes, and I absolutely believe that. I've seen that. The reason this works is the $500 award is not going to change a student's life, but it's something to get some credibility. But yeah, I think if the awards increased, it would be quite. You'd see people trying to game the system, and that's very dangerous. So yeah, I'm not being critical from the standpoint that I don't think all these initiatives aren't useful, but I'm just saying that there's such a payoff once you go completely open, make all parts of it open, that you gain a lot more. But that's just my opinion.
Some of the other kind of open projects are global rivers and things like this. I would urge somebody to share some of the ones you like. But basically every elementary school around the earth that you could collect rainfall data, temperature data, things like this. That think of it that we have many more school children than we do have technologists, and what's the kind of fine-grainedness that we can get if we want to talk about global warming, that if all of a sudden the amount of data that we're accumulating is almost exponentially increased, we have a much finer-grained kind of system. And various kind of people have been doing this kind of thing. And part of the critique has been that in so many cases, the students are simply used as kind of data gatherers, but they don't have a conceptual sense of how this might be used, for instance, in a debate of global warming or global warming kind of data and so on. And how is it that the user community that's contributing becomes part of establishing what's the more important data to collect, how is that data going to be used, how is it that there's policy that's made up on this kind of data. And so the kind of pioneering work that Dr. Bradley has done is here the data is open, the contribution is open, the algorithms are open, the models are open. This is a fully open model. And it's hard to find models as open as yours. I do a considerable amount of effort trying to look for this kind of thing. And so in some cases, just you find that even in open access publishing, that people are playing cute and clever games to hide things in plain sight. And that, yes, it's open and available, but it's more like it's an advertisement for what their lab has accomplished, rather than that you have enough details in that openly published model, for instance, for you to duplicate or reproduce the work and so on, kind of thing. So I'm curious, how would you feel in your classrooms about all of your students' data being live and open the minute they collect it?
Actually, one thing that people who haven't done it criticize, I think it's happened once that a student didn't want to use their full real name. I mean, that actually surprised me, but because I've done other things that I haven't shown here today, like students writing essays on the wiki openly, and it kind of, I would have expected maybe 20% or so. I explained it, they have the option of using a pseudonym and emailing me, what corresponds. And I think it's only happened once, and that's the world that they grow up in. They expect everything to be freely available, and they're shocked, some of the undergraduates, when they start working in chemistry, that, hey, this is actually not completely free, and you have to go through some paywalls, and you have restrictions about, things that you can do. But so that is one thing. If you're worried about your students, not liking, they actually like that for the most part. I do think you have to give them a very, very clear option that it's not mandatory. You have to do that, ethically. But if they do accept it, then yeah, they can, when they're applying for jobs or whatever, they can link back to their live notebook pages, anything that they've produced in the class. So yeah, it'd be good.
Anybody performed some experiments or tried, or are there open sources that you value, or? Yes, please.
I just have a question, sort of philosophical question. So I don't have any problem with putting students' data, having that open, but what about the entrepreneurial opportunity? So somebody's doing a lot of work and they want to start a business. It's sort of...
Right. So, that's the first thing is when the student comes to apply to work in my lab, there will be no patents. That's just basically, it's incompatible. The way we operate is incompatible. Some people disagree with that, but basically it'd be extremely difficult to get any kind of protection. So, but students don't really even know about the patent system typically. But yeah, I have not had a student not work in my group because everything they were going to do was in the open. That's never happened. And we have no interest in commercializing any of this. This is where you start to have different objectives instead of just pure science. I've done that. I used to patent everything that I could, but I realized that I was just losing too much of my work working that way, and that's why I switched over to becoming open, so that the 87% of the stuff that never should, that the world would never see, actually it gets used. So yeah, it's incompatible, but that doesn't mean that you couldn't monetize this if you think about it differently. So first, you can't think about selling data. You can't think about selling models. I mean, you could think about a company that would use all these open feeds to customize for a company. I could see that. I mean, one of the things, for example, our melting point prediction algorithm, I'm a co-editor at Chemistry Central Journal, and one of the things that I've put in is when they submit a compound with a melting point, our model predicts, and if it's over 30 or 40 degrees, we flag it. And so now, because there are errors in the literature about melting points, and we could stop most of them if we simply did that, and that's an open data feed. It's a prediction, melting point prediction. And we've caught some errors like that, and you want to catch them before they go to print, and that's something I think that every chemistry publisher can use. And that could be an example where they would pay a company to set it up. I mean, once it's set up, it's completely free. So I don't know. I'm just thinking out loud, but the opportunity is not in the intellectual property for this.
I would refer you to a book called BioBazaar. It's by Janet Hope, and she talks about open models in the biotech industry and where companies have used trademarks, secrets, patents, etc. And the other reference is Larry Lessig on Code 2.0. This is a law professor at Stanford University who's been trying to rewrite American patent law because in today's technology that the patents are good way too long and it prevents too many other people from doing creative kinds of work. And so instead of, say, a 17-year, moving to a 3 or 5 year in terms of some kind of things, it would still give companies a competitive advantage to get up and get going kind of thing. But the Supreme Court is actually considering a gene patent law now that may change all of patent law in a quite large thing. But in my biophysics class, I had my students had to design and build something and then write a patent application. And it was just, for me, I thought part of their professional education, important for them to have that. And a number of my students over the years have started companies and have patents and so on. But my own stuff is I publish by copyleft and open access and a variety of other kinds of things. But I think for my students, that's their choice in some kind of cases. And that as an educator, I feel obligated that they know what the options are. Roger, please.
I have a rather large archive of biological images on the internet, which I receive requests for, continually. Also had some offers to market these. I would send all my images to a place and they would market them. I'd get a percentage of whatever they got. I decided I didn't want to put up with that hassle. So, my policy has been, if you're going to use these for educational purposes, please feel free. If you're going to use them to publish a book and you're going to make a buck, then I charge them for it. But I'll tell you, just the thanks that I get and the gratitude I get from some people that use these images, it's enough payment for me. It really is, just to know that I've been some use to people in their educational pursuits all over the world. It's just wonderful.
So Roger, a young scientist last week in Science was interviewed in terms of doing all of his PhD work in this kind of open model, and might he not be scooped and all of this and that. And what he said was the benefit as an early age that he had of forming a scientific network of, as you said, people thanking him and so on, and even, pointing out failures in some of his protocol, but also helping him out kind of thing. That today many of our students are more open to this kind of network kind of model. And how do you build a social network early on in your career? And so here this individual promoted it from that standpoint. That what are the assets in an academic culture of free and open exchange?
Yeah, one point I would make, that there's been a hot debate as to whether you should slap on a non-commercial application, and I have become strongly of the opinion that you should not. That if you make it, see, the problem is it's not clear what commercial is, and you have a lot of people that you wouldn't consider it to be commercial, but they're saying, well, let's say someone is working at a university. A university is a place of business. And if they used it, so what ends up happening is the people you want to use your stuff don't because they're scared. And it turns out that there's so few people. I mean, nobody's going to take your stuff and make $1 million by because anyone can already access all your material. So I would just say that consider making it open data, and you might actually get more people using it without any of the downside that you fear. That's just the opinion I've come to after seeing people try to use that non-commercial clause. It's really tough.
If you go to the Creative Commons website, they have about 7 levels of open publishing. And the most common one is simply that you give attribution to the source kind of thing. Yeah. But, in other kind of cases, it's freely available without even attribution.
Yeah, for actual data, like melting point numbers, it makes no sense for attribution because it would be unmanageable. But, yeah, I think we have CC BY for the lab notebook pages, which makes sense. We just need an attribution. But yeah, for data itself, a lot of people have been discussing that, and I'm completely of the opinion that you have to make it, for Creative Commons, CC 0 is really the only option that makes any sense.
Anybody have some open projects that you're doing or running?
Another interesting thing about the patents is if you keep an open notebook, you should be able to prevent people from patenting in a specific area. And that's actually something that I've become quite interested in, because we worked in the malaria field, and it turns out that we came across some patents on some work that was similar to what we were doing, and if we had done those experiments 3 years earlier, I talked to the people at Creative Commons and Scientific Commons, and it appears that actually would hold up because it's so easy to find the information. So this is kind of flipping the script on the whole patent area. I mean, you could even use it aggressively. I mean, if you had a competitor, you could actually prevent them from patenting stuff that you're afraid to, and it would cost you nothing as opposed to you having to patent it to prevent them from getting a patent. So there's a very quick and dirty way I think that companies, would be using that. And so if you go back to models, I think people who would be skilled at that could actually set up businesses, with that kind of approach. So all of these things just open up new possibilities, and the whole patent area, as you said, is very tricky, but there's some unintended consequences that can happen.
I mean, just listening to this conversation, it seems like there's just two fundamentally different ways of looking at this. Is there any way that you parse the kinds of things that would be subject to open source as opposed to things that might be better considered to be intellectual property and protected?
Well, for myself, it's just not worth, doing something, because I get contacted by people who want to collaborate, and that's usually where there's a problem. Like when I switched to this, I had to change my collaborators because it would be very unusual that everybody would change their mind at the same time. So, but then once you find that, you're never going to convince those people to want to start patenting the work that you're collaborating on. So, yeah. So basically, where I am right now, it would make no sense for me. Like I get offered, you write a book chapter that's going to be closed source. I got to balance that against something that I could do that's going to be open. So everything sort of falls in the open area because my time is limited, so I'm going to spend it. But there are people who I could easily see could have a project open and another project with these collaborators that is completely closed. I see no problem with that. I just personally, that's just my position. But yeah, it's a project by project based thing, I think.
Spoken? Well, I think let's cut it off there, and then those that would like to stay and have more personal conversation, this is fine. Thank you so much. Next week we will be talking about, if I write, iPads in the classroom. I think we'll have probably speakers from about 5 different departments participating at that time. But please feel free to have more food and come and interact with us. I think the issue of openness, note that in our ancestors that many teachers operated on a model that they got paid for their lectures by individual students, and that their tricks of the trades were highly hidden and so on and kept very close to the vest. And now most of you work in an educational environment where people put out their best ideas for helping students learn, and that you routinely borrow from one another in this kind of a system. And so that while some research endeavor is still highly commercialized, that most of us who are involved with teaching have freely and generously given away our best secrets all of our careers, and feel honored if somebody does borrow something that we have done. So thanks very much for participating in this discussion, and please feel free, food and more conversation. Thank you very much.